Recording in progress.
So, hi everyone, my name is Archit Sanjan and I'm going to be teaching complex numbers today. I'll be following the syllabus that is mentioned in the JEE Advanced 2025. Okay, and so as you can see in the screen, uh, the first thing that I want to show is like I want to create a base for the complex numbers. And so we'll first see what set numbers that we have seen so far in our earlier classes from like way back in class 1 to UKG. Have used so many numbers. They now will be divided into real and imaginary. Right. So like real numbers are all the numbers that you have seen so far in your life till now. Right. All kind of numbers that are real, like like there's one bottle, there's two apples, there's anything that has any real meaning or real representation is called a real number, like one, two, three, four, all the integers, all kind of fractional numbers, your whole numbers, all kind of numbers that you can think of are called real numbers, right? Sorry. And the second part is the imaginary number. So the imaginary number is basically something that does not have an like real meaning or something. Okay, it was basically uh, mm, it it basically came from uh, like what happens if we what happens like for example, if we say that under root of 4 is 2. But now here it is always 2, not minus 2. Okay. So it is important to note. Like it is under root works only and only if there is a positive number inside the root. So what happens if we say I want to know the value of under root minus 5? We don't know, right? So just to represent what is the value of under root minus 5, because this is an like good question, right? What happens if there's minus 5 inside? So to represent this, what we did was we created a number called iota. Sorry, iota, which is basically under root of minus 1. So this number can be represented as under root of minus 1 times 5. Right. This will become under root of minus 5 times iota. So this is an imaginary number. Anything or any number that has an iota inside it, um, with it is called an imaginary number. Right. So it is quite clear, right? What is an imaginary number? Anything that has an iota multiplied with it is called an imaginary number. Right. I don't think there's much need of any like going much further deep inside it. That is it. Okay. So next, I like to show you what is a complex number. Right. So as you can see, we have an z which is a complex number. Right. It is basically uh, okay. Let me just hide it. Yeah, fine. So complex number, right? So z is a complex number, and it is basically a combination of a real number and an imaginary number. Right? It has two parts, real part and imaginary part. So this is how we generally represent an complex number. And A and B here both are real numbers. Like any real number, both of them are real numbers. And B here is basically multiplied with iota. And so this is I believe that's like skimming the layer for the complex numbers and not like going very deep since it is an inter class. Right. So now here it is important to note that what happens if we like A and B are real numbers, right? So they can take any values. So let us say we'll put A as 0, that's just for experimenting. So if we take A as 0, we'll get Z is equal to iota B. Simply. So this is a number that does not have any real part in it. Right. So what do we call this? This is a purely imaginary number. Right, fine. And similarly, if we take B as 0, we get A, a real number. So now we can say that all real numbers are basically complex numbers. Such complex numbers which do not have an imaginary part is called a it is called a real number. Quite simple. So we can say that Z or a complex number is basically a superset inside which is real numbers. So like complex numbers, real numbers. Fine. And it is important to note that B is a real number and iota B is an imaginary number. Although I'll be using this real part and imaginary part again, people do get confused here, right? Okay, so now since we have seen what is a complex number, we have seen what is an imaginary number. I like to get going with the algebra of complex numbers, right? What is the algebra of complex numbers? Basically, the addition, subtraction, multiplication of a complex number. Very simple. So now, okay, now first of all, you must think like obviously when we are going to add two complex numbers. Let's say we have Z1 and Z2. So if Z1 is A1 plus iota B1, Z2 is A2 plus iota B2, where A1 B1 A2 B2 are real numbers. So what if we add them? So I have written the result as this A1 plus A2 plus iota B1 plus B2. Basically, I'm trying to like separate the real part and the imaginary part time and again. Because when we are going to compare two complex numbers, we are basically going to compare them using the real part and the imaginary. Because like from common sense, right? If two complex numbers are the same, like if Z1 and Z2 have to be same complex numbers, then they have to have same A1 and same A2. Like A1 has to be equal to A2 and B has to be equal to B2. Only then we can say that these two complex numbers are similar or same. Right? So that, like it is not something like a certainty that you have to write write it like this. But generally, we try to attack it because it seems organized, right? And similarly, if I go to subtract these Z1 and Z2, we get even my C2 plus I have B minus B2. Simple subtraction. And now it is important to note here that we are not mixing the imaginary part. We are not going to like solve the even plus I to be even one. Just actually a complex number. There is nothing simpler than this. There's no simpler form for a complex number than this. Okay, right. So now if we move on to the multiplication, let me show this. Yeah, multiplication of two complex numbers. Now multiplication can actually be mixed, right? We can have a multiplication of imaginary number and a real number because when we defined complex number, as you can see, when we defined complex number, actually we had a multiplication of complex number, imaginary number and a real number. Iota is an imaginary number, right? Iota is simply an imaginary number which has no a, like no a, I mean a0 and b1. Basically, imagine iota is also an imaginary number. So if we have an example of multiplication of like two complex number and b is also a complex number, so we can actually have something like iota b. So based on that we'll be doing z1 into z2. So what is z1 into z2? Basically we'll be multiplying z1 and z2 together, and obviously we get a1 times a2, right? We get a1 a2. We have a1 times iota b2, which is a1 b2 and iota. Obviously, we can open this and we will do the same thing. Similarly, iota b1 into a2, we get iota a2 b1. Right. The only thing that occurs new is iota b1 into iota b2 is minus of b1 b2. Where is the iota? So basically, if you properly think, right, what was iota? Iota was under root of minus 1. If we square these two in this iota, we get a minus 1 out of it. So, and that is where we actually get minus. Quite simple, right? So this is actually one that usually people forget by multiplication that iota square does change the sign. Just keep it in mind. Fine. Finally, now will be going towards the conjugates of a complex number. So if you remember your quadratic equation part, you will remember that let's say we have an quadratic equation of the form ax square plus bx plus c is equal to 0. Excuse me, I think I missed this. Okay. Right. So we usually have a solution for this. That is x is equal to minus b plus minus under root of b square minus 4ac, right? 2a. For simple, right? So uh, and this is called the discriminant of a quadratic equation, right? So when we had d is equal to 0, we had a real and like same solution, right? Only one solution. When we had d positive, we had real and unique solutions, right? But what if we have d equal to negative? If you remember, we had d equal to negative. We had imaginary and conjugate complex numbers as a result. So what's the conjugate complex number? Basically, if I have z is equal to a plus iota b as we have taken earlier, then z then let's say yeah then z yeah so z bar is something that we'll be choosing to represent the conjugate of complex number is basically a minus iota b. Basically, let's just swap the sign. And if we had z is equal to a minus iota b, its conjugate would have been a plus iota, a plus iota b. Basically, switching the sign of the of what separates the real and imaginary number, right? Okay, so now once we have understood what z bar is, the conjugate is, we can actually use this to kind of understand what um real part and imaginary part of complex number is uh, using the conjugates and the yeah this right. One thing that I would like to inform you once again, going from here, is that here one important thing to notice: what is the modulus of a complex number, right? So modulus of a complex number is basically, let's say we denote it with r, or it's also denoted written as z r. Say z is equal, let's say we choose z1, then z1 is equal to z bar, z modulus is basically equal to a square plus b square. You will basically understand this much further just the in the next part. I'll just show you. Just remember, this is basically the modulus of a complex number, right? Modulus correct. So while we take the modulus, it is important that there exists a triangle inequality, which basically states that z1 plus z2, both modes, is basically greater than z1 plus z2. Quite simply, this is the triangle inequality. Rest of the things are quite similar to what we have seen as model as an absolute positive value. No much difference, right? If you actually see complex numbers, they're quite logical. No very big twists and turns exist in their mathematics, right? Just one point. I'll just show it my photo again when we actually see the graph of a complex number, right? So fine. Let's see again. So we had this, and but actually trying to show the real. Okay, fine. So what would be like the real part and the imaginary part of complex number? So far, you may have got confused that imaginary part is actually iota b, but no, the real part is a. A is a, right? Okay, a is the imaginary number and the imaginary part Sorry, I got confused. Sorry, my mistake. But A is a real number and a real part of the complex number also. But B is the imaginary part of a complex number, although it is a real number. It is quite very important to see here that A is a real number and B is also a real number. But actually, B is an imaginary part of a complex number. Fine. Let's go ahead. So, how do we get now? We try to generate a formula or an equation for the real and the imaginary part. Right. Okay. So we'll be denoting real part of a complex number. Let's say we have Z as a complex number as RE of Z. Okay. So RE of Z is basically A, right? So what we can do to generate A from A plus iota B and A minus iota? Simply add both of them and divide by two. We get the we 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 get A, right? And if we add A and A, we get 2A. Iota B and minus iota B gets cancelled and we get 2A. And hence we have to divide it by 2. So it is actually what? Z plus Z bar divided by 2. Okay. Similarly, okay, let's write here, right? I can adjust it yourself, right? So the imaginary part of Z or I of Z is equal to B. That can be found using Z minus Z bar by 2. Sorry, 2 iota. Not I because we will have an iota on that. It has to be removed. Okay, quite simple. Okay, now seeing this 1 by iota, I can also we can also see that 1 by iota can also can be shown as this also. Right? Let's give some box. This what would be the multiplicative inverse of iota? So obviously 1 by iota, right? And it can also be written as minus iota. It just works sometimes using when during your JEE advanced. Sometimes they give a question where you don't see a pattern, and you just have to convert the 1 by iota into minus iota, and then you can see a pattern coming. So this sometimes gets missed, but it's quite simple. So I would suggest to convert them as soon as you see, but it is generally easy or simpler to see this rather than this. This does give an odd kind of view to the problem, right? So this is important. Now, once we have seen the conjugate, also we can see something interesting here. What happens if we multiply both of them? We saw the addition, we saw the division, we got the real part and the imaginary part. What if we multiply them? Both of them are complex numbers. Let's see what happens if we multiply them. Right. Okay. So Z times Z bar. Right. What happens if we do this? Okay. Now sometimes you can get a question. Let's say, what is Z double bar? Like if I give a double bar, it is simply Z. Right. No, not a big fuss about it. Simply Z. Z bar ka bar is Z. Simple Z. What's the conjugate of conjugate? The number itself, right? Quite simple. Right. So we have decided to set bar. What will be the answer here? A plus iota beta B, sorry, mistake. Then A minus iota B, simple multiplication. A into A is A square, right? A into minus iota B, so we'll get A B minus iota plus A B iota, right, from here, and then B square and a minus, and I square also gives a minus, so minus minus plus. We get a B square. This gets cancelled. We get A square plus B square. Does this ring a bell? Yes, to you somewhere. If it does not, let's see. Where was it? Here. Basically, the modulus came out. So this is basically r square. This is a very important relation which comes to use very often during the questions in J8 ones. So z into z bar is z square. Sorry, r square. Pretty important. Fine. So I think I have so far covered most of the topics, most of the general topics of complex numbers regarding their conjugates, their addition, multiplication, all things, right? Subtraction also. So let's move out now. If you see, we are generally trying to develop a mathematics around the complex numbers, like just like we did when we are young. Like we first studied the for the we then studied what is 1 plus 1, 2 plus 2, or 1 minus 1, 1 minus 2, all the things we got. We then moved on to multiplication, like 2 times 3, 4 times 5, all those things. Now, then what we saw, we did in your class 6.7 or somewhere, or younger, I don't know. We got graphs, we got the coordinate geometry, we got straight lines. So we are going to try to generate these things for complex numbers. Now it is very evident that we don't know, or we don't have any so far. We don't have for the tools that we have so far seen. We don't have any coordinate plane or the Cartesian plane that can plot imaginary numbers. These real numbers, it is very easy, right? We have seen the coordinate geometry, all this fine. But what about the imaginary number? It's a problem. So for this, we actually made a new plane for plotting the complex numbers, which is called the Argand plane. Yeah. Just let me zoom out a bit. Yeah. So this is the Argand plane. Uh, at the first glance, you can see that it is not very complex, simple 2D plane which plots the real part and the imaginary part of a complex number. See, that does not need to be plotted. It is there. The things that vary for a complex number is a and b. So the imaginary part b, the real part a, and if you do some calculation, you will get the second root of h of the b square from Pythagoras theorem, and this is basically r, right? So and that is if we consider z is equal to a equal either b, right? Consider this is simply the r plane. And from here, I like to see what about this angle? There's an angle that is subtended by this complex number z on the real part or the real plane. What about that? Let us say it is theta. Theta. What about that? Now, here, it is important to note all thetas that we'll be seeing here are to be measured in radian and not in degrees, right? So what about that? What do we do for from theta? So if you remember from your early classes, uh, we have actually seen that we can if in some parts the Cartesian plane was not useful for us for the questions or the topics, we use a polar coordinate system. Well, what was the polar coordinate system? If it basically something that had like a straight line here, straight line here, we had an R here, so I put a straight line, it is not straight, and we had a theta angle here, where basically x came out to be r cos theta, and y came out to be r sin theta. This was the polar coordinate system, right? Same thing we'll be using for the complex numbers. That is the polar representation of a complex number. This. This is the polar representation of this number. Basically, what we will be doing is we had z is equal to a plus iota b, right? So here from the earlier full order system, what we saw that a would become r cos theta and b would become r sin theta. Quite simple. And if we now convert this, we put these values into the earlier equation for z. We get z is equal to r bracket cos theta plus iota sin theta. What is the best? Right. Now this is the polar representation of z. Okay, now once we see theta, what we want to see here is like what theta should we take? And theta is there, but what if we turn around and come again? This again is theta, right? Same theta, same. I mean, the cos theta value won't change if we take a whole circle, or if we take another circle. Again, it won't matter. You take n number of circles, the same value will come. So what do we do? Like so far so good. We had a and b, which will give us a unique value of a and b, will give us a unique z. Hence, we can like separate z, right, from all things. But now once we have this, like cos theta of pi by 6 will be the same thing. 2 pi plus pi by 6 will be the same thing. So we'll have multiple representations of the same set. It will give you complications, confusions, right? So to like solve this problem, we introduced principal arguments. What is the argument? Fine. So theta is called the argument of a complex number. This theta is set as argument. Now this argument can take n number of values from 0 to all things, right? You can go in a circle and continue to get new value for the same theta. So how to fix this? We introduce a term principal argument. Principal argument is a theta which lies between minus pi to pi. Right. So what can we see here? This is let's just extend this a bit. Right. So minus pi is this, right? This is minus pi, and this is pi. So minus pi to pi. You have to go here to here. Do you understand now? I know it got into a mess. Let's just remove this. Right. Sorry, extra. So this is basically a minus pi. This is pi. So any value that exists in between these two is called principal argument. Right? And this is the only theta that will be generally used when using the polar coordinate system. Otherwise, it will be very confusing. Right. Let's move on now. So this is just simple. Okay, now, yeah. So Euler went one step ahead and said, I can simplify this further. How? Well, what about this term? We can now just simply say, I will determine cos theta plus iota sin theta as e to the power I theta. Now said as again a new form, r into e to the power I theta. This is a Euler form for an complex number. I got cut off. Let's just leave it there. Right. What's left? So we have so far seen complex numbers, their polar representation, their conjugates, their graphs, all are fine, right? Now what do we do? Now, yeah, there is one topic left is to go to infinity. But before we go to that, and that is almost the last topic for this video. Before we go there, we'll have one more thing. I like to give you a very like, good looking question. Right? What do you say? What would be the value of I to the power I? What are iotas, not i's, right? So to solve this, we can do one thing. It sounds confusing, right? What we do about this. So only just to solve this, just we'll try to use a Fuller representation. And what we do here is we had z equal to r into e to the I theta, right? For the z, that was a plus iota beta. So r was basically a square plus b square, 20 root, right? That's theta was something. So what about iota? It is a complex number, right? It has it's a complex number, but a is equal to 0 and b is equal to 1. So where will iota lie in the organ plane? Iota would lie somewhere here. The imagine line. So what is the angle that this iota subtends on the real part? Pi. Sorry, pi by 2. So this is another important thing. All purely imaginary numbers will subtend pi by 2 angle on the real part, real line. Right? And all the purely real numbers will subtend 0 angle on the real line. This is an important thing to know. So we can represent I, now since I has 0 and 1, R will become 1 for this, right? So Z become, Z or I becomes e to the power I pi by 2. Quite simple, right? P and pi by 2 does lie between minus pi and pi. So this is the representation for iota. Now what we do, we put this into this. This gives us e to the power iota pi by 2 to the power iota. That is, sorry, e to the power I plus I and I because I squared left technically minus of pi by 2. This is the answer. This actually gives you headache when you try to solve it using a plus iota b and do all those rubbish. Simple. E to the minus pi by 2. Okay. And now we'll be moving on to the last topic, the cube root of infinity. Infinity? No, not infinity, but cube root of unity. I try to just change my mistake. Cube root of second. Yeah. Cube root of unity, not infinity. What would be what will we be doing of infinity, right? Nothing. So unity. And what is unity? One. We are going to try to find the cube roots of unity. How? Good question. Let's proceed. So x cube is 1. So how will we do? How will we find cubes? Now it is important to note that cube root of since x has a power 3, it will have 3 roots. The roots can be imaginary, real, that is fine. But it will have 3 roots for sure. So let's try to solve this, right? Let's try to factorize this into simpler terms. So it will become x minus 1 into x square plus x plus 1 is equal to 0. Just shift the 1 to LHS and break it up. So from this we get x is equal to 1 and x square plus x plus 1 is equal to 0. So we got one root as x is equal to 1. That is fine. We got one. So the roots that we get will be right here. Roots. We got a 1. Now what? To solve this, we'll be using the formula from our earlier discussion. What was the formula? X square plus 1 sorry, of this. But we'll be writing this into the solution part. That is x is equal to minus 1 since b is here. A is 1, b is 1, c is 1. So minus 1 plus what will be the discriminant for this? Will be b square minus 4ac. B is 1, so b square is 1. 1 minus 4 into a is a into c. It is 1 minus 3. Sorry. sorry, 1 minus 4, that is minus 3. So minus 3 by 2a, 2. That is fine. So we get this as x is equal to, okay, plus minus 1. So minus plus root 3 by root 3 iota by 2. We get the minus 1 outside. Sorry, root 3 outside and minus 1 control will be iota. And the other result will be minus 1 minus root 3 by 2 iota. Now, obviously, it's remembering these things are quite tedious. It is not good looking. We are mathematicians. We try to look good. So what we do now? So we call this as omega and this as omega square. So there are three roots. One is omega. One is one is omega, and the last one is omega square. Right. So uh, now you can ask why we have used omega square instead of like omega 1 and omega 2 because it is actually a square. And you can see that let's say we multiply these two things, right? Let's say we multiply minus 1. What was the first what would you use as omega? Minus plus, right? Actually, you can actually switch both of them. Like either one of them can be omega square and either one can be omega. Both are possible. So plus root 3 by 2 iota. And I'm going to square this. We get 1 minus 3 because iota square is minus 1 plus 2, not plus but minus 2 into root 3 and 1 by 4. So we get minus 2 root 3. We divide by 2, so we get minus 1 minus root 3 by 2 iota, which is omega square. So this gives us three roots, that is, here, sorry, 1 omega and omega square. Now, obviously, they have some properties, right? Properties of the polar unity. What would be the property? Okay, right. Before we go to properties, we have to see one more thing because we have to use polar representation. So we can actually break this into two parts. Like what would be the real and imaginary part? So the real part would be let's just say like open it fine. So omega can be what minus 1 by 2 plus root 3 by 2 iota. Similarly, omega square can be omega square can be minus 1 by 2 minus root 3 by 2 iota. And now just think and tell me if I want to represent these two into their respective polar representation, what would we do? So the first thing for the polar representation is R. What would R? Square. Square then add them. So 1 by 2 the square is 1 by 4 plus minus root 3 by 2 or add any of them. They the same square. So 1 by 2 ka square plus 1 root 3 by 2 ka square is right? 3 plus 1 by 4. That is 4 by 4. And so R comes out to be 1. R square R. So we don't have to double this with R anymore. So omega is equal to e to the power I of derivation that is left is theta. So what theta will give us cos theta as minus 1 by 2 and what theta will give us as to c theta it will have sin theta as root 3 by 2. So if we divide them into the Cartesian plane, but what we remember is here all are positive, here only sine is positive, here only tan is positive, and here cos is positive. So the place where this is cos is negative and sine is positive. This part, right? Obviously. So we'll have theta as uh, pi by 3 plus what? Pi by 2, obviously. So we'll have pi by 3 plus pi by 2. That is 5 pi by 6. So 5 pi by 6. Then similarly for omega square, you can find the values for where both sine and cos both are negative. So the part. Use that. Fine. Once we are done with that, we can now move on to their properties. Right. So properties are quite easy to get, understand. What we used was x cube minus 1 is equal to 0. Now, if we compare it to like try to find the sum of them, right? What will be the one sum of 1 plus omega square plus omega plus omega square? Is basically the sum of roots, right? What is the sum of roots? Minus b by a. What's the value of b? 0. This is 0. This is first property. What's the multiplication of these three things? 1 into omega square. This is omega cube, right? Omega cube is what? Minus of c by a minus of minus 1. Therefore, omega cube is 1. These are the important things. And okay, one more thing. Omega is based from here, we can actually derive that one omega is actually also the multiplicative inverse of omega. And the reverse is also implied, right? So these are three properties that one must remember for the complex numbers or the Q root of infinity. And we can actually like expand this to the nth root of infinity. And it is very easy to find. The same way that we solved x cube minus 1, we'll be going for n minus 1. And just opening this thing. Quite intuitive and quite simple to solve. Okay. Sorry. So omega first property is 1 plus omega square equals 0. The second is omega cube is equal to 1. And from there we can actually show that omega is equal to 1 by omega square. Done. Right? So thank you. Once again, I'm Masih Sanjan. I'm student of IIT Patna. I'm currently in fourth year. Thank you.